Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. In this video, we talk about two important topics that you need for understanding machine learning problems. The first one is matrix multiplication, and the other one is finding inverse or pseudo-inverse. So if you're interested in this topic, please keep watching and don't forget to like and subscribe. In a previous video, I talked about NumPy and creating one-dimensional and two-dimensional arrays. In general, NumPy array is something that is very useful for machine learning problems because compared to Python list, it allows us to have arrays of numerical values. And that's very useful because machine learning problems, we work with numerical values. Therefore, NumPy offers array computing, mathematical functions such as finding exponential, finding sine or cosine, or other types of functions that you have seen in calculus. We also have linear algebra routines such as matrix multiplication, finding inverse, and finding pseudo-inverse, and similar topics that we will see a few of them today. And here in this video, we are going to start with two-dimensional arrays. And if you want to understand more about the difference between one-dimensional and two-dimensional arrays, please watch the previous video, and I put a link in the description below. So a two-dimensional array is something that we call it a matrix in linear algebra. A matrix has a form like this, matrix A here, where we have n rows and we have m columns. So the way that we can think about this is that we have n rows. So this means that we have n vectors or one-dimensional arrays that they are stacked together horizontally, right? So that's row number 1. And then this is row number n. Or similarly, we can think of these as m one-dimensional arrays that are concatenated vertically. So then this would be column number 1, and this would be column number n. So we can use rows or columns. And each element in this matrix, let me just erase this so we can now see better the elements in this matrix. And now each element in this matrix, if we look at it, has two indices. So the first one shows the position in the first direction, and the second one shows the position in the second direction. And remember that when we talk about linear algebra and mathematics, we usually start indexing from 1. So this means that we have n rows and m columns. But when we are using Python and NumPy, it is more common to start indexing from 0. And therefore, then the row number would be from 0 to n minus 1, which means that we have still n rows, but it's just you have to subtract each of these numbers by 1. So this is just something to keep in mind when you're working with NumPy. But for now, we are mostly talking about mathematics, and linear algebra. So here, for this reason, we start indexing from 1. So as you see here, this element here is in the nth position in the first direction, and then in the second direction is the first element. So that's why it is an1. And then this element here, we have it in the last position in the first dimension, and similarly, it's in the last position in the second dimension. So that's why it is ANN. And the way we show that this two-dimensional array is by using this notation, which means that we have real valued numbers in general. And then the first one is the number of rows. And then the second one is the number of columns. So that's something that we use a lot. And it is also common to just write this as n by n. So that when we say a two-dimensional array is n by m, it means that it has n rows and m columns. So that's the general definition of a two-dimensional array and how we are going to index them. So next, we are going to create two-dimensional arrays in NumPy and start working with them so you see how these things will work out in Python. As we have said in previous videos, in these videos, we use Google Colab or Google Collaboratory. So it is a very nice tool provided by Google that you can start using Python and other packages such as NumPy without installing these packages on your own machine. So this is sort of like something that you use in your browser, and you have to do zero configuration, and you also use Google's computing resources. In order to use Google Colab, it is very much similar to Google Doc. You just need to go to colab.research.google.com, as you can also see here. And then you create a notebook. Here, I just call the notebook as Dr. Data Science notebook. That's why we have this IPYNB. So that's a Jupyter notebook, if you're familiar with that. And then you can just immediately start importing libraries and modules that you want, and you don't have to install anything, and they are regularly updated. So here I'm going to import NumPy. And remember, in general, you can import NumPy as is without using the second part, or you can import NumPy as, and then a shorter name here, and it's very common to use NP. So this allows us that anytime that we need to use something from NumPy, then we can just use NP rather than NumPy. So it is definitely up to you that if you want to just import NumPy, or you want to import NumPy as the name that you want, which is the common name is to use NP. And it's always a good idea to check the version of NumPy that you have. And that's what we have here, which is print np dot double underscores version. And that gives you the version that we are currently working with this. So now you know that how you can use Google Colab. I definitely recommend you to copy paste everything that we have here in a Google Colab so you can exactly see how that works. So one thing that is important is to understand the idea of access in NumPy. And here we're creating a two-dimensional array. And the way that I create this is by first creating a one-dimensional array using np.arrange. So when you say np.arrange 12, that means that we get a one-dimensional array with 12 elements that we start from 0. So we get 0, 1, 2 to 11. But it obviously has 12 elements because it starts from 0. And then I use dot reshape, and I put this in a two-dimensional array with 3 rows and 4 columns, as we just talked about. So one thing that it is important to notice here is that when you're working with NumPy, you can even have higher dimensional arrays, meaning that arrays that they have 3, 4, or 5 dimensions, or even more. And for that reason, it is not really possible to just give names to all these different dimensions, because in the two-dimensional case, we know that this one is called rows, and then the second dimension is called columns, right? So then the question is, what if we have 3 dimensions or 3 axes? Then what should we call the third one? So in order to solve that problem, it is common to just give them numerical value. So the way that it works is that the first one is this one, which is axis equal to 0. And then this is axis equals to 1. And then if you want, you can also have, for example, axis equals to 2 and 3 and 4 when you're working with higher dimensional NumPy arrays. And in order to understand how this works, for example, you can use NP. You remember we imported NumPy as NP. That's why we have NP here. NP.sum. And then we have the name of the matrix A here. And if I choose axis equals to 0, that means that I want to sum the elements of this two-dimensional array along this axis, which means that I'm going to have 4 numbers. The first one would be 4 plus 8 plus 0, which is 12. And the second one would be 1 plus 5 plus 9, which gives me 15. And then similarly 18 and 21, right? But also, if I want, now I can add the elements of A with respect to this other axis, which is axis 1. So I pause here for a second so you can now think about it and see how that's going to work. So you can see that because axis 1 is this one, right? So this means that now we are going to add the elements along this axis. So obviously, now we will have 3 elements, right? So the first one would be 0 plus 1 plus 2 plus 3, which gives us 6. And similarly, these will be other values that we get here. So we can sum the elements of a matrix with respect to the axis equals 0 or axis equals 1. This is very easy to use if we have more than 2 dimensions, right? We have, like, let's say a 3-dimensional array. That is going to be very useful, for example, in image processing or computer vision applications. But the idea here is that to understand what axis means when we are working with NumPy arrays. So now we are going to review what we had in the previous video that I told you that I'm going to put the link in the description below, and how we can use simple linear algebra to find matrix multiplication. And one of the easiest form is that when we are multiplying a 2-dimensional array, such as like what we have here, which is, let's say, 3 by 4, and then we multiply these by just a vector that has 4 rows and 1 column. So the way that we can do matrix multiplication is that we are going to make sure that the neighboring dimensions, they match. And if so, this means that this matrix multiplication exists, and the result would be 3 by 1. And now, in order to find the first element, what we are going to do is that we are going to find the inner product or dot product between the first row and this vector here. So this means that the first one will be A11, B11, and then A12, B21, A13, B31, plus A14, B41. And it is very easy to understand how this works. These two numbers are always equal. So that's like the general way to find this, right? So you can also, for example, look at this second element. In order to find this, you're going to find the inner product or dot product between the second row and this vector that we have in the front. So this gives us A21, B11, A22, B21, A23, B31, and A24, B41, right? So if we look at it, these numbers are again identical. And we can continue this process. But what is important here, how this works in NumPy. So here I created a 2-dimensional array A, and you can see that here. That's the array that we had in the previous slide. And then now we create another 2-dimensional array. So the way that it's going to work is that we're going to have numbers from 3 to 7, and 7 is excluding. So that's why we get 3, 4, 5, and 6. And then we're going to reshape this. So now the first one is 3 by 4, and the second one is 4 by 1. So we obviously have 4 rows and 1 column. And now we can use np.matmul, matrix multiplication, and then you give these two matrices in the same order. So meaning that here we want to multiply A by B. So that's why we say np.matmul A and B. And I'll just check the first element to show you that it works. So it means that we have to find the inner product between these two. So 0 times 3 is 0. And then we multiply 1 by 4. And then 2 by 5. And 3 by 6, which this would be 18, 10, and 4, which gives us 32. And that's what we expected to get. And you can continue this process to make sure that this matrix multiplication is correct. But obviously, it is correct because that's what NumPy gives us. So that's like one of the easiest forms of matrix multiplication, that we are multiplying a two-dimensional array by another two-dimensional array which has only one column. And if you are, for example, look at some textbook, that's usually the formula that you see. So if you look at it, this formula, even though may look complicated, is easy to use because what it is just simply this inner product. And remember that even in the previous slide, we said that these two numbers are always identical. And they go from 1 to n. So that's why we have a summation of a1i bi1. So that's for the first element, up to the element number m, which would have this form. And if you're wondering why we have m elements, because here we have m rows and n columns. Here we have n rows and 1 column. So the result would be m by 1. So now the question is, what if we have more than 1 column in this matrix in the front, right? So obviously here now we have m by n, and then we have n by 2. So we know that if this second array has only 1 column, we can use this way of defining inner products between each row and the vector that we have in the front of the first matrix. But what should we do here? And the solution is very similar. So what you do, if you really want to understand how this works, you can assume that one time you're going to multiply these two together, and another time you're going to multiply the first one by the second column, and then you're going to concatenate these results. So here in this slide, we explain this process. So we have the first column here, and then we have the second column here, and we already know how to do each of these matrix multiplications, and we will have the results for each case. And now we're going to concatenate these two vectors. And obviously this approach is slow and it doesn't really scale very well if we have more than 2 or 3 columns, but it is important to use this to understand how this works, and it also helps you to better understand how machine learning algorithms work when you have matrix multiplication. So that's why we are going to first focus on this approach, which we call it the slow approach. So in order to understand this, we have a matrix A, which has 3 rows and 4 columns. So it is 3 by 4. And then I create another two-dimensional array, which has 4 rows and 2 columns. And what we have done here is that we're going to, again, use that np.mathmul, matrix multiplication, to multiply A by the first column of B, and that's where we have this indexing here. Remember, indexing starts from 0, so that's why here we have B, and then we have comma 0. So that means that the first column, and obviously this one means the second column. I write this here, so this is the first column of B, and this is the second column. So we do this multiplication, and we find each of those results. And now the next step is to concatenate them together. And so in order to do that, you can use np.concatenate. So in NumPy, there is a built-in function that you can use for concatenating arrays. And if you remember, we have, I'll just go one slide back. So that's what here I call that C1. And this is the one that we call it C2. And now we want to put these two things together along the axis equals 1, if you remember, when we define axis. That's exactly why we discussed about the axis in two-dimensional arrays before. However, if we do so, you see that we get an error message that says that axis 1 is out of bounds. And so you may wonder what's happening here. So that's what we discussed in the previous video that I discussed, that in general, it is very important to understand difference between one-dimensional and two-dimensional arrays. The way that some of these functions work, sometimes you may have two-dimensional arrays, and they give you back a one-dimensional array. And that's exactly what is happening here. So if you look at C1, it has 3 elements, but it is actually a one-dimensional array. It's not a two-dimensional array. And for that reason, when we say axis equals 1, NumPy gets confused. It says that, oh, we don't have more than one axis here, so it should be just axis 0. And so in order to fix this problem, it is relatively simple. So we go through all these steps to find C1 and C2, and then we need to convert those one-dimensional arrays again to a two-dimensional array. And the way that we can do this is using this simple trick that we can use dot reshape, and then we use -1 and 1. So what this means is that it means that we want to have one column, and we let NumPy to figure out how many rows we need. So this means that, for example, for C1, we have these 3 values that now they are in a one-dimensional array, but we are going to put them in a two-dimensional array that has 3 rows and 1 column. And similarly, so then the C1 would be 28, 76, and 124. So now NumPy recognizes this as a two-dimensional array. And then we have C2, which is 34, 98, and 162. And now we are going to concatenate them along axis equals 1. And that would be the result that we get, as expected. So that's something important to keep in mind anytime you're working with NumPy arrays, to understand when NumPy recognizes them as one-dimensional or two-dimensional arrays. And if you want to convert a one-dimensional array to a two-dimensional array, you can always use dot reshape, and then you can use a trick like this one, where we say that we want to have one column, and NumPy will figure out the number of rows. That's why we put -1 here. However, you don't have to follow this approach, because this is the slow approach to understand how this works. And when you want to use NumPy, even in this case that, let's say we have 3 rows and 4 columns and 4 rows and 2 columns, you can still use np.mathmul, matrix multiplication, and just give the name of these two-dimensional arrays, and it will automatically calculate the output for us, which is identical to what we got in the previous slide. So if you look at this, this is exactly the same result as what we got before. So in general, the takeaway here is that when you're working with two-dimensional arrays and you want to do matrix multiplication between two-dimensional arrays, use np.mathmul. So here, I want to also show you a trick that's going to be extremely useful when you're working with large-scale data sets. So let's say we have 4 two-dimensional arrays, and here we call them A, B, C, and D. So, and the way that we create them here, because again, here we're just trying to show how this matrix multiplication works. So we fill in these two-dimensional arrays with random numbers. So that's why we are going to use np.random. That's a module that has a lot of random number generation techniques. And then we are going to basically create metrics filled with random numbers. So we don't really here necessarily pay attention to what those numbers are. It is just more about how the matrix multiplication works. And if you look at it, is that the matrix A, right? So matrix A has 10,000 rows and 1,000 columns. And matrix C has 1,000 rows and 10,000 columns. So if you multiply A by B, you see that it would be a 10,000 by 10,000 matrix, right? And then if you multiply A times B by C, so that A times B is 10,000 by 10,000, and C is 10,000 by 5, and then at the end we want to multiply. So here we see that A times B times C, it would be 10,000 by 5, right? Because the neighboring dimensions match, and the result always would be this. And then finally, for D here, we have 5 by 1,000, which means that the final result would be 10,000 by 1,000. So here I want to show the difference between using different matrix multiplication techniques. The one on the left, I'm going to use a method that may be more straightforward. So what we are going to use is that we are going to import time. So this will allow us to find elapsed time to run some lines of code. And the way it works, we define a start and end. So both of them, they will measure the time. So that's what and at the end, we are going to just subtract end by a start point, right? So that will tell us like how long it took to run these lines of code or to do these matrix multiplications. And in the first one, we are going to multiply A by B. So that's where we make that 10,000 by 10,000 matrix, which is really big here, right? Because we have a square matrix, and obviously creating a 10,000 by 10,000 matrix, it's going to be costly. And then the result is going to be multiplied by C, and then we are going to multiply the product of A by B by C and by another matrix, which is D here. And we see that this takes about 6.5 seconds. However, if you want to do this faster, it is a better idea if we do not multiply them from left. So what this means is that we have this A times B times C times D, right? So it means that I can multiply C and D, so I find this, and then find B times C times D, and then we multiply it by A. And the advantage of doing this is that we never form a matrix of size 10,000 by 10,000, which that's sort of like the computationally expensive part. And because this can be in general like a challenging task to do, to identify which way it is better to multiply these matrices, that's why in NumPy, there is a module called linalg, which stands for linear algebra. And that has very useful functions. And one of them is this multi_dot. So the way that this function works is that you just give a list of all these arrays that you want to multiply together. And this function is very smart. It's going to figure out how to multiply them faster together and avoid, for example, forming very large matrices as we just talked about. And the advantage is very noticeable here. So when we do this multiplication using this multi_dot, we see that this takes only about 0.1 second. So if you think about it, this is almost 60 times or higher a speed up compared to the first approach. And as you're going to work with larger and larger data sets, for example, let's say this matrices A might have like millions of rows or even more, then the sort of like the difference between these two techniques would be even more substantial. So that's something to keep in mind, that in order to do matrix multiplication between different arrays, this function, which is multi_dot, which is part of np.linalg, is very useful. Okay, so now that we talk about matrix multiplication, we're going to talk about another important linear algebra tool that we need, and that's matrix inverse. So in order to understand this, let's first talk about inverse. So if I give you a number, let's say 2, and I ask you what's the inverse of this number, you're going to ask yourself, what should I multiply by 2 to be able to get 1? And obviously that number is 1/2, right? So the inverse of 2 is 1/2. It is also common to write this as 2 to the power of -1. So we want to have a very similar object when we are working with two-dimensional arrays or matrices. Therefore, consider a square matrix. So that's very important, because if you have a matrix that is not a square, and here also let me define what a square matrix is first. So a matrix is called a square if it has the same number of rows and columns. So that's why here we show that using this notation n by n. So the number of rows and columns are the same. So if you have a square matrix, and if you want to find its inverse, which here we showed using this notation A inverse, but this is not obviously 1/A, because that doesn't make sense for two-dimensional arrays. In general, what this means is that we are looking for another matrix A inverse or B, such that A times its inverse, or inverse of the matrix times the original matrix, gives us the identity matrix. An identity matrix is right here. Identity matrix is generalization of 1 to two-dimensional or arrays or matrices. So for example, if n equals 3, then the identity matrix would be a 3x3 matrix, which has 1 on the main diagonal, and then the rest of elements are zeros. So this is exactly like what we have here, except the fact that now we have multiple ones on the main diagonal, and then the rest are, of course, zeros. So inverse of a matrix is such that if you multiply A by its inverse, or multiply the inverse by A, you get the identity matrix. So it has exactly the same meaning as, or I would say like the same intuition behind it as when you find the inverse for just a single number, which we call it a scalar. So we want to multiply a matrix by its inverse and be able to get identity matrix. And remember that that matrix should be a square matrix. So now let's look at this, how this works in NumPy. So we create a two-dimensional array A, and then that's again the module that we just talked about it. So np.linalg.inf. So that's the one that will compute the inverse. So we had originally a 3x3 matrix, so it was a square matrix, and now the result is still a 3x3. And now let's see if we multiply A by B, whether we get identity matrix or not. So if we calculate this using matmul, matrix multiplication, that we just talked about it, we just saw that we get this result. And you see that on the main diagonal, we get these ones. That's exactly what we want. I just created here on the right-hand side how an identity matrix of size 3x3 looks like. And you see that here on the off-diagonal terms, we have terms in the order of 10 to the -16, -17. And so this is something common that can happen. So here, if we look at it, for us, A times B is almost identical to identity matrix. And we have a very, very small amount of error, which we call it like sometimes like machine precision, because these numbers are like technically very, very close to zeros. And this can happen. So for us, we can say that yes, A times B is equal to identity matrix, even though we have very, very small deviations from a perfect identity matrix. So here we created the matrix, we computed its inverse, and we confirmed that matrix times its inverse is equal to the identity matrix. However, the bigger question here, and something that we have to pay attention to it, is that does the inverse exist all the time, or should we be concerned about the existence of matrix inverse? And that's a great question, and the way that we can figure that out by measuring something that is called determinant, which is a scalar or a single number. So when you have a square matrix, you can find its determinant, and if the determinant is equal to 0, then that matrix doesn't have an inverse. So here I created this matrix A, which is again a two-dimensional array of size 2 by 2. We have 2 rows and 2 columns. And you can use np.linalg.det, which means that we are finding the determinant. And we see that the determinant is equal to 0. Now I know that if I use np.linalg.int, then the inverse doesn't exist. And that's exactly what Python tells me. So you see that we get an error message, and at the end it says that this is a singular matrix. So a matrix that has determinant 0, that's a singular matrix and does not have an inverse. So this is something important to keep in mind, because you may work with some machine learning algorithms. At some points, you have to find the inverse, and you may see an error message that says singular matrix. And you need to understand that what's happening here is that you have a matrix that the determinant is equal to 0. So now, if we're talking about pseudo-inverse, I want to talk about something else that is called matrix transpose, which is very easy to understand. So here, I'm going to create, again, a two-dimensional array, which has 2 rows and 2 columns. And the way that you can find the transpose is just by switching rows and columns. So that means that matrix A, the first row is 1 and 2. So now for the transpose of that, the first column would be 1 and 2. And similarly, now the first or the second row is 3 and 4, and now the second column would be 3 and 4. And in order to find the transpose, you can either use A.transpose or just use A dot and then capital T. So it really depends on which one you prefer. And obviously the first approach, which is A.transpose parentheses, it will give you more options if you're working with high dimensional arrays and so on. Now, as a practice, you can see what the transpose of the matrix B will look like, or the two-dimensional array B. And here we have 3 rows and 4 columns. So here we see that if we find the transpose, then we will have this row in the first column, and similarly the next row in the second column, and third row in the third column. So remember that in general, when we have, for example, here a matrix with 3 rows and 4 columns, which is 3 by 4, then the transpose will be 4 by 3. So this means that if we have an n by m matrix, after finding transpose, this would be m by n. So now we can talk about pseudo-inverse. Now, one of the easiest way to understand pseudo-inverse is by looking at a linear equation. So think of that as having this matrix A, right, which has m rows and n columns. So obviously, when m is not equal to n, the matrix A does not have an inverse because it's not a square matrix. But in a lot of cases, we have like a system of linear equations, like here, where A is given, and theta is n by 1, and B is n by 1. In these cases, we have A and B, and we want to know what theta is. So there's no way I can find A inverse. So how can I solve this problem? So what you can do is you can multiply both sides of this equation by A transpose. Remember that A transpose would be n by m, right? Because we changed the number of rows and columns. And this will give us an n by n matrix. So now we have a square matrix, which is A transpose A. And here, as long as this matrix is not singular, we can find its inverse. And we can multiply on both sides. So this means that we get now, I can show you in one more step here. So we have A transpose A theta, and then we have A transpose B. So I can multiply both sides by A transpose A inverse. So this gives me identity matrix. So identity matrix is equivalent of 1. So when I multiply identity matrix by theta, I get theta. And then I have A transpose A inverse A transpose B. And then this term, so everything here except B, so that's what's called the pseudo inverse of A. So when A is not a square and you want to find its inverse, we can use the this sort of idea of pseudo inverse. And this is also implemented in np.lineout. So here I created a matrix or a two-dimensional array A, which is 3 by 2. And then we find the pseudo inverse, which would be now 2 by 3. And let's multiply the pseudo inverse, which is B, by the matrix A, and see whether we get something close to the identity matrix again. And you can see that here we have very close to the identity matrix of size 2 by 2. So if you look at it, the diagonal elements are almost 1, and then the off-diagonal elements are almost 0. They're like 10 to the power of negative 16. And to just understand why we get a 2 by 2 matrix, remember that B is 2 by 3 and A is 3 by 2. So then the result would be 2 by 2. Therefore, pseudo-inverse is something that is something that you can find for matrices that are square or they are not a square. And you see that in a lot of machine learning problems. And one of those cases is linear regression. I have another video that I discuss linear regression in details, but here I'm just going to show you how just understanding pseudo-inverse allows you to perform linear regression. So in order to explain that, let's work with, again, NumPy. So I'm going to import NumPy as NP, and you have everything that you need to implement this in Google Colab. And then for visualizing purposes, we are going to use matplotlib. And from matplotlib, I'm importing pyplot. So here I'm creating a two-dimensional arrays. So the first column, these are the x values, right, or the independent values. And then the y-axis are given in the second column here. So these are the dependent variables. And the goal is to find the relationship or connection between the dependent variable and an independent variable. So therefore, in this line, we are separating them. So this is the first column, that's the second column, and we give them the name x and y. And we make sure that x is actually a two-dimensional array. That's, again, that trick that we use with x.reshape. If you want, you can just call it -1, and Python will automatically figure out how many rows we need, or you can use this len, length of x, and this will find that out. And then we're going to use the scatter plot. So you see here we have like 5 data points. So we have the x and y values for these 5 data points, and we're trying to find the best line that fits this data set. So obviously, if you pick like two of these points and draw a line, would be different for each case, right? So therefore, the goal is that what is the best line that will go through this data set? So the reason that I said that this is very much related to that pseudo-inverse problem, because what we're trying to solve here is that x times theta, we want to be as close as possible to y, right? So we have x, we have y, and we are trying to figure out what theta should be such that x times theta is as close as possible to y. So the way that we can solve this is by simply finding the pseudo-inverse, which is that P if you remember, of x, and then we multiply this by y. And that's exactly what we have here, right? So what we are finding is pseudo-inverse of x in NumPy, and then we're going to use np.mathmul to find theta. And after we find theta, that's the parameter that we have, now we can use the data to make predictions, right? So we now just give our inputs, and we multiply it by theta, and this gives me the predicted values. So here now we have the scatter plot as what we had before, those 5 circles or points, and now we have also plotted this red line, which we just calculated based on our predictions. So just understanding pseudo-inverse and being able to find that is what we need to solve a linear regression problem. And this example just shows that how easy that process is. So I really hope that you find this video useful, and you'll definitely see a lot more about matrix multiplication, inverse, pseudo-inverse, and transpose working with machine learning problems, and I will have future videos on those topics. And please don't forget to like and subscribe. And if you have any questions, please let me know, and I try to get back to you as soon as possible. Thank you so much for listening.